Saxon Advanced Mathematics. We're in the middle of lesson 47, ladies. We talked about vertical sinusoid translations. I'll give you a little spoiler hint. When I have to pause my video in the middle of a lesson, it usually means I have a pet that is demanding my attention and I need to deal with them. So thank you for being patient. I also kind of like when there's a break in the lessons because it gives you a chance to kind of collect your thoughts and breathe, and it's way easier to upload shorter videos. So that makes my technical demands easier to cope with. All right, so now we're going to look at part B, which is about arctangent, or the inverse of tangent. Before we dip into this, let me just do a little bit of review to get your feet on some solid ground. Recently, we have talked about the reciprocal trig functions. They are different than this. Remember, the reciprocal trig functions are created by taking our old friends, and let's start with sine. If we take 1 over the sine function, we call that cosecant. And we can think of it this way, or we can just take sine and flip it, and it becomes hypotenuse over opposite. All right? We know that we can take 1 over cosine, and that has a special name. We call that one secant. And that, again, we take the letters for cosine and we flip them. So that one looks like that. Okay? And then we can do the same for tangent. If we take tangent and state it as a reciprocal, we call that one cotangent. And that, instead of being over Arthur, it's Arthur over, right? Yay, Arthur wins. So these, notice, these are the same sides for the original parent functions. We just flip them because we're taking the reciprocal, right? So John sometimes uses this notation. You can think of it that way. I prefer to think of it this way. I think it's a little easier, but it all means the same thing. So those are the happy days, right? This one, I'm just going to write the names out. This one is called cosecant, secant, and cotangent. Okay, I want you to remember the names, but we abbreviate them. And remember that the little trick for remembering which one goes with which is that each pair of reciprocal functions has one C and one S. All right, so mix them up. As I said, in a future lesson, we're going to learn, because look, sine and cosine, secant and cosecant. That's an interesting parallel in the names, isn't it? We're going to figure out what those names mean and why they have that co prefix on them and how that relates. So that's a fun lesson. All right, these are the reciprocal trig functions. They have nothing to do with this. This is what we call an inverse trig function. We learned about these way back in the day when we were talking about the calculator buttons, right? And we said that you use the button that says sine and cosine and tangent, right? These are my calculator buttons. We use those buttons when we know the degrees of the angle that we're measuring, and we want the decimal, which is the ratio of the particular sides, right? And when we're using our calculators, it gives us that ratio in decimal format. So that's where this expression came from. This is my expression. John didn't come up with this one. It's when we know the degrees and we want the decimal, which also represents, sometimes it's a fraction or a ratio of sides. We think of it that way. Then we have these other buttons that have this -1 thing going on. Right? And I said that doesn't mean it's a negative exponent, because that's what's so confusing. This looks like a reciprocal function, right? Because sine to the -1 would be 1 over sine. That's confusing. But the buttons, the people who came up with the buttons, I think need a good hard slap across the face, because they made it way more confusing than it needs to be. These are what we call the inverse functions. And P.S., these are called the parent functions. They're like the basic ones, right? Okay, so those are the parent functions. And then the inverse functions are what we use when we know, now I'm going to confuse you just a little bit, when we know the decimal, or again, the ratio of the sides. And again, this is often expressed in a fraction. Same for this one. It's often expressed in a fraction. And we're going to see that again in just a minute. And in these, we want the degrees. We want to know how big the angle is, right? Okay, so that's what an inverse function is. It's working backwards. Normally, we know the degrees and we want the decimal, but with an inverse function, we know the decimal and we want the degrees. We're going to work these problems not using our calculator, so we don't have to worry about the buttons, but we're going to start with the ratio of the sides using our friendly little 30, 60, 90, and 45, 45, 90. So it technically won't be a decimal the way we're expressing it, but we're going to start by knowing the fraction and we're going to figure out the degrees. Okay, now here's the thing about the inverse functions. We're finding the degrees, but we know that because, let's say we have a 30-degree angle right here. We know that we could call that a 30-degree angle, or we could spin around an extra time and call it a 390-degree angle, right? Because it would be 360 plus another 30. Or we could call it what would be next, a 750, right? So we know that we could keep spinning around and come up with an infinite number of these names that have the same, what we call a terminal angle. And these are all considered to be coterminal, meaning they end at the same place, right? So we don't want a bunch of coterminal angles. We just want one angle as the answer to our inverse functions. So we've come up with a cool way to symbolize that and to wrap our hands around this problem. And the way we have done that, okay, the problem is that we want to prevent naming, I don't know why I put that as a capital, let's pretend it's lowercase, to prevent naming an infinite number of coterminal angles we limit solutions to 2 quadrants per function. Okay, so here's our graph. All right, so we say that if we're trying to find the inverse angle of cosine, or let's start with sine. If we're looking for an inverse function of sine, we know it's going to be a certain number of degrees. We only want to name one angle. So we're going to limit it to the first quadrant, which is where the positive solutions of sine will be found. And then we're going to take the fourth quadrant because we have to be able to find our negative values too. So for sine, the two quadrants that we use are the first and I'm going to use Roman numerals, the fourth. Okay? The positive ones will be in the first quadrant. The negative ones will be in the second quadrant. And we use those same quadrants for tangent. Because in the first quadrant, tangent is positive, and in the fourth quadrant, tangent is negative. So for tangent, we can limit the two quadrants to be the first and the fourth also. Now, with cosine, we have a problem, just a little bitty problem. Cosine is positive here in the first quadrant, so that's cool. We'll use the first quadrant for cosine, but we can't use the fourth quadrant because cosine is positive in the fourth quadrant. So we have to come up with another solution for cosine because if we limited it to first and fourth, we wouldn't have any place to identify our negative cosine values. So what we do is we jump over to here to quadrant 2, where cosine is negative. All right? So, to prevent naming an infinite number of coterminal angles with inverse functions, we limit the solutions to 2 quadrants per function. And by that I mean cosine, sine, cosine, and tangent. 2 quadrants, 1 positive and 1 negative. For sine, we choose the first and the fourth. For tangent, we choose the first and the fourth. Check, check. Cosine, it doesn't work, so we have to go sideways instead. All right? And we pick up this one. Another way that we can write these is for sine, we say we want the values to be, let's see, how do we usually note this? Let me write it a different way with more space. We say that they're between positive 90 and minus 90 degrees because this is 90 up here, right? And this is 0. And we can call this negative 90 or 270. And then we can call this 180. So for cosine, we say they're between 0. I think that's the way it's usually done. The equal to signs I'm not 100% sure of. This is between 180 and 0 because cosine is this way. And then for tangent, it looks just like sine. All right? So this is sharing. This is the same information as this. It's just saying which are the 2 quadrants that we choose for the solutions of inverse functions. And again, we want to get 1 positive and 1 negative quadrant for each function. 1 and 4 are the obvious choices for sine and cosine. Tangent has a problem with that, so we have to give him another solution. Cosine's the little diva, all right? This you've all heard before, but you know what? When I first told it to you, you were just getting the hang of this, and so it's hard for it to stick. So I'm going through it again so that you can hopefully let it sink in just a little bit deeper, all right? So this is where we're going to pick up. These are inverse functions, and what we're going to do in this section is just practice doing an inverse tangent function because there's a fun little wrinkle in this problem. Okay, let me just, no, I'd like to do it here so that we have all of our notes in front of me. All right, 47.3, and there's just one problem for this. It says evaluate, and then it says that's the thing we're supposed to ask for. And what it's saying is it wants to know the angle measured in degrees whose tangent is the tangent of 135. And we look at that and we just go, what? Isn't it just 135 degrees? Tell me the degrees of the angle whose tangent is 135 degrees. It seems like it should just be 135, right? Don't those cancel each other out? Well, let's look and see. So we want the tangent of 135 degrees. So here we go. That would be second quadrant, right? 90 and 45, so we're halfway through. There we go. 45, 45. It's the cute little easy one. Let's put in the sides. The legs are each one, and this is square root of 2. Tangent is equal, the tangent of, we'll call this theta, right? That's what we often do. We use that as our mystery. Instead of x, we often use theta, as you're seeing, for our angles. The tangent of theta is equal to, it's over Arthur, right? And the tangent is 1 over 1, right? And tangent in the second quadrant is negative, right? So it's negative 1. And so that tells us that theta must be 45 degrees, right? Because that's the degree measurement of the angle that gave us this picture. So we say that theta equals 40, but it's not 45, it's I'm sorry. Once we get this value, we can say now we want the arc tangent of -1, right? Because this plugs in, this became this. We found out that the tangent of 135 is -1. So now we want to find the arc tangent of -1. And that means we're looking for, we have to limit our angle now, right? This is the trick of the problem. With tangent, we can't have a second degree or a second quadrant angle. We're not allowed based on the limits we've given ourselves. So in order for us to have an angle whose tangent is -1 means we have to go to the fourth quadrant. So this is the angle that creates a tangent of, right? This is the one that we need. And so the final solution to our problem is -45 degrees. So what this all boils down to, you guys, it was a kind of a confusing problem because John's trying to make the point that if you're trying to find the answer, the degree measurement of an angle, it's gotta be in those specific quadrants. And if it's in one of the quadrants that doesn't allow for these, that doesn't include in the solution set, then you have to flip it into either the positive or negative quadrant, depending on which one you need. We needed negative. You have to plop it into the right quadrant and reconfigure the angle. So even though it seemed like the angle whose tangent is 135, it seemed like this should obviously be 135. We can't use that as a solution because it's in the second quadrant. We had to flip it to the fourth quadrant, and that is the right answer. All right? That's kind of a little parlor trick. That's kind of a weird little problem that pops up. It's a good reminder of how these limitations work. All right. We are done. I'm going to see you for lesson 48, and we're going to add a new wrinkle to our trig function problems. It's easy. Don't worry. Bye.